Hey, grade 11s, as we're working towards understanding how to calculate work, another thing that we're going to look at right now is elastic potential energy, which is very, very common and is part of one of your simulation projects. Elastic potential energy would be energy stored in elastic materials like the spring over here. If I stretch or deform materials, I have to do work against some type of property that wants that material to come back to its original position. And that energy, or that work that I put into it, is going to be stored as potential energy and can be used to do other types of energy conversions, such as kinetic energy or work on other objects. So here, a spring which is made by winding metal into a coil, I can then tune how stiff that spring is by looking at the diameter of the metal or how many turns I have or the radius of those turns. And then I can program potential energy by stretching or displacing it. So in this topic, we're going to learn how to calculate the work that I do onto those springs when I stretch them or compress them. I'm going to learn how to apply conservation of energy like we did last year to then see how that work can be transformed into other things. And we're going to calculate work and energy from graphs. So the first thing that we want to look at is how do we calculate work with a spring? Well, it takes energy to stretch or compress springs. So here I have a spring at its equilibrium position. And if I pull that down, this is my displacement from equilibrium. So how would I calculate how much work it's going to take for me to pull that down? If I analyze the force, the graph would look like this. As I pull it down, my displacement on the bottom, as I pull it down, the force increases like this. Okay, so how would I go about calculating the work? Okay, well, if I remember what work is equal to the product of force and my displacement, okay, or distance. So here on one axis is force, on the other axis is my displacement. If I look at that equation, what it's telling me to do is to multiply force by displacement. And what that will give me is the area under this graph. So the area is equal to work. Okay, so the area under a force displacement graph is going to be work. And notice that it's a triangle shape. So in order to calculate that area, what this graph is telling me is 1/2 times force times displacement is equal to work. That's what the graph is telling me. 1/2 comes from the fact that this is a triangle. 1/2 base times height. Base is x, height is f. Okay, and we know that F for springs is equal to kx. So it's really telling me, all right, so force is kx. It's really telling me that. So if I multiply that through, 1/2 kx squared is equal to the work. And what we've done right now is we've derived a formula for springs to calculate the elastic potential energy of springs. So the elastic potential energy of a spring can be written as this, which I believe is in your data booklet. That's an important formula to know. So you want to write that into your texts or into your notebooks. Okay, so 1/2 kx squared would allow me to figure out how much work I have to do to stretch a string, where k is the k constant of the spring and x is my displacement by how much I pull it. Okay, and now you know where the 1/2 came from. So let's try it in practice. Calculate the work required to stretch a 100 Newton per meter spring by 10 centimeters. Well, the formula is, so my elastic potential energy, which is the work that I have to do, is equal to 1/2 times 100 newtons per meter times 0.1 meters squared. Okay, and if I multiply that product together, I should be able to get 5 joules, I believe. Yeah, I think that's about right. Let's quickly do that on my calculator. I don't have my calculator with me, so you'll have to just trust that that probably is what it's going to be. Okay? And then let's take a look at conservation of energy with springs in a loaded system like a pinball machine. Okay, so the elastic potential energy stored in a spring can do work on objects and be converted into kinetic energy. Okay, so I presented this in class where we had a pinball machine. If I pull back the spring, I'm going to be doing work on the mechanism. And that work is going to be stored as elastic potential energy, which is 1/2 kx squared. Okay? And then if I let go, that elastic potential energy can be converted into many things. It can be converted into kinetic energy, which has a formula of 1/2 mv squared. So the mass of that ball times its velocity when it leaves. So all that elastic potential energy is going to shoot that ball out and give it velocity. Okay, and then that kinetic energy can be converted into gravitational potential energy. So if I'm looking at an object going straight vertically up, that would be work done against gravity. Or if I'm looking at the object going up a ramp, it's going to be mg sine theta times the distance that it goes up the ramp. Let's just change the color here. Okay, I'll call that D. Okay, so mg sine theta, because that would be the force of gravity, the resultant force of gravity pulling that object down the ramp, times the distance that it goes up, okay, would be the work done thanks to kinetic energy, which was thanks to the elastic potential energy. And the last thing I need to think about on a pinball machine is work against friction. So that kinetic energy, that kinetic energy is coming to do work against friction. All right, now what force are we talking about? Well, we're talking about the frictional force. Okay, and how would I calculate frictional force? Well, you remember it's going to be mg cos theta, which is my normal force, times my friction coefficient, times d. Okay, and d being the distance it goes up the ramp. All right, so these are all different conservation of energy situations where we start with elastic potential energy and it's converted into many things. And I can create a model to figure out how high that ball is going to go up a ramp based on its angle, which I have in my formulas, okay, and based on gravity. All right, I'll be able to calculate d where it ends up, and that's what you're going to be doing as your simulator task. You're going to calculate the distance a pinball would travel up the ramp in the image, not below, but above. Okay, so if I'm going to copy this image, place it here, if it allows me. Okay, so I can then calculate the distance that that ball is going to go up. If you pull the spring mechanism back by 5 centimeters, the mass of the ball has 100 grams, okay, and the angle of the ramp is 11.8 degrees, and the coefficient of friction is 0.2. I should be able to go back to these formulas and figure it out. What would D be in that situation? So I want you to pause the video and see if you can try to put it all together.